Before we dive into this video, it's worth being upfront about something important because a lot of recent chatter online has gotten this story tangled up with misinformation. There is no brand new 2026 course change happening with Oumuamua right now. The object is currently so far from the Sun and so faint that not even the James Webb Space Telescope can detect it anymore. Several viral posts and blog articles claiming Oumuamua has turned back or returned toward us are simply false, unsupported by any real observational data, and not backed by NASA, the European Space Agency, or any credible research institution. What this video is actually about is something far more interesting than a fake headline. The genuine, well-documented, still unsolved mystery surrounding the one real course change Oumuamua underwent shortly after its discovery back in 2017, a subtle but very real deviation from its expected gravitational path that scientists spent years trying to explain, and which, in certain respects, still isn't fully settled today. So, let's set the record straight and take a proper deep dive into what actually happened, why it confused some of the best astronomers in the world, and why this small, strange visitor from another star system remains one of the most talked about mysteries in modern astronomy. To understand why Oumuamua's trajectory became such a big deal in the first place, you need to go back to October 2017, when astronomers using the Pan-STARRS-1 telescope in Hawaii spotted a faint object moving through our solar system on a path unlike anything they had ever confirmed before. Almost immediately, calculations of its trajectory revealed something extraordinary. This object wasn't orbiting the Sun the way every comet and asteroid native to our solar system does. Instead, it was following what's called a hyperbolic trajectory, meaning it was moving too fast and on too straight and open a path to ever be gravitationally captured by our Sun. It had clearly arrived from somewhere else entirely, from interstellar space, having formed around some other star, possibly billions of years ago, before eventually being ejected from its home system and drifting alone through the galaxy for an unimaginable length of time, until it happened to cross paths with our own Sun. This made Oumuamua the very first confirmed interstellar object ever detected passing through our solar system, and its discovery instantly became one of the biggest astronomical stories of the decade. Its name, chosen by the Hawaiian astronomers who found it, translates roughly to scout or messenger, fittingly capturing the sense that this object was the first of its kind to reach us, a lone envoy from somewhere far beyond our own cosmic neighborhood. From the very beginning, Oumuamua behaved strangely. As astronomers around the world scrambled to point every available telescope at it during the brief window, it remained observable. They measured its brightness changing dramatically and rapidly as it tumbled through space, a pattern that suggested an extremely elongated, unusual shape, some estimates suggesting it was up to 10 times longer than it was wide, comparable to a cigar, a surfboard, or possibly even a flattened pancake-like disk, depending on which model astronomers applied to the brightness data. No object remotely like this had ever been observed before, either within our own solar system or from beyond it, and its bizarre shape alone was already enough to generate enormous scientific interest and public fascination. But the shape wasn't even the strangest part of the story. That distinction belonged to its motion. As Oumuamua continued its journey through the solar system, swinging around the Sun and then heading back out toward interstellar space, astronomers meticulously tracked its position over several months, comparing its actual observed location against the trajectory predicted by gravity alone. Under normal circumstances, an object's path through the solar system can be calculated with remarkable precision using nothing more than the combined gravitational pull of the Sun and the planets. But when researchers compared Oumuamua's predicted path against where the object actually turned out to be, they found a small but genuinely significant discrepancy. The object was accelerating slightly, ever so subtly speeding up as it moved away from the sun in a way that pure gravity simply couldn't explain. This phenomenon is what astronomers call non-gravitational acceleration, and while it isn't unheard of in astronomy, the explanation behind it in Oumuamua's specific case turned out to be genuinely puzzling. To understand why this small trajectory anomaly created such a stir, it helps to know that non-gravitational acceleration isn't actually a mysterious phenomenon on its own. Comets throughout our own solar system display this kind of behavior all the time. As a comet approaches the sun and warms up, the ice on its surface begins to sublimate, transitioning directly from solid to gas. And this outgassing process releases jets of material that act like a very weak natural rocket thruster, gently nudging the comet's trajectory away from the path pure gravity alone would predict. This is a well-understood, thoroughly documented process, and astronomers routinely account for it when tracking the orbits of comets native to our own solar system. Given that Oumuamua displayed this same kind of subtle, unexplained acceleration, the natural first assumption for many researchers was that it, too, must be an active comet, quietly venting gas and dust as it was warmed by sunlight, just like millions of other comets scientists have studied for centuries. But here's where things got genuinely strange, and where Oumuamua's mystery truly began. When astronomers searched for the telltale signs of cometary outgassing, specifically a visible coma, the glowing cloud of gas and dust that surrounds an active comet's icy nucleus, they found absolutely nothing. Despite intense, repeated observation using some of the most sensitive telescopes available at the time, Oumuamua showed no detectable coma, no visible tail, and no measurable dust or gas emission of any kind. This was a serious problem for the simple cometary explanation. If Oumuamua's acceleration really was being caused by outgassing, the same physical process responsible for producing comas and tails in every other known comet, then astronomers should have been able to detect at least some trace evidence of that gas and dust release. Instead, they found an object that appeared in every visible respect to be a bare, inert rock, and yet was somehow still accelerating in a manner that closely resembled the behavior of an actively outgassing comet. This contradiction, an object behaving like a comet while looking nothing like one, is precisely what pushed Oumuamua from being simply an interesting scientific curiosity into becoming a genuine, widely publicized mystery. Naturally, this unexplained gap between Oumuamua's observed motion and its observed appearance led to a flood of scientific proposals, each attempting to explain the discrepancy through entirely natural means. One of the earliest and most widely discussed theories suggested that Oumuamua might simply be releasing gas and dust in quantities too small, or in a form too fine for existing telescopes to detect, even though this same process was still strong enough to produce a measurable nudge in its trajectory over time. Researchers also proposed that Oumuamua's unusual, highly elongated shape and its complex, chaotic, tumbling motion, rather than a simple, steady rotation, could have played a role in scattering any outgassing material in ways that made it far more difficult to detect, using conventional observational techniques, essentially spreading out any dust or gas release so thinly and unevenly across the object's tumbling surface that it never produced the kind of concentrated, visible coma astronomers typically expect to see. Over the following years, one particular theory gained significant traction within the scientific community, eventually becoming one of the most widely cited natural explanations for Oumuamua's strange acceleration. Researchers proposed that Oumuamua might be composed largely of frozen hydrogen ice, an extremely volatile substance that sublimates or transitions from solid to gas at temperatures far colder than the water ice found in most comets native to our own solar system. According to this hypothesis, sometimes referred to as the hydrogen iceberg model, an object made significantly of solid hydrogen ice could produce enough outgassing thrust to explain Oumuamua's observed acceleration, while still releasing so little visible dust and gas that it would remain effectively invisible to the telescopes tracking it, neatly resolving the apparent contradiction between its comet-like motion and its asteroid-like appearance. This theory drew considerable scientific interest because it offered a plausible, entirely natural mechanism, one grounded in known physics and chemistry, capable of explaining both aspects of Oumuamua's strange behavior simultaneously without requiring any exotic or unconventional assumptions. Other researchers have proposed alternative natural explanations along broadly similar lines, suggesting that Oumuamua might instead be composed largely of frozen nitrogen ice, a material also known to sublimate readily, and one that scientists have separately proposed as a possible building block for certain classes of icy interstellar fragments, potentially chipped off the surface of Pluto-like dwarf planets orbiting distant stars. Under this theory, a relatively thin, nitrogen ice-rich outer layer could account for Oumuamua's observed acceleration through gradual sublimation while still remaining too faint and too efficiently vented to produce the kind of easily detectable coma astronomers were searching for. Both the hydrogen ice and nitrogen ice explanations share a common thread. They attempt to identify a specific volatile material capable of producing meaningful outgassing thrust while staying largely hidden from direct telescopic detection, essentially threading the needle between Oumuamua's comet-like motion and its stubbornly asteroid-like appearance. Not every researcher, however, found these outgassing-based explanations fully convincing, and this is precisely where Oumuamua's story took its most famous and most controversial turn. Harvard astrophysicist Avi Loeb, along with a small number of other researchers, argued that the observed acceleration, combined with Oumuamua's extraordinarily unusual shape, its complete lack of any detectable coma, and several other subtle anomalies in its behavior, collectively pointed toward a more radical possibility, that Oumuamua might not be a natural object at all, but rather some form of artificial structure, potentially an alien probe, drifting through interstellar space, or even something resembling a light sail, a thin, flat structure theoretically capable of being accelerated by pressure from sunlight itself, rather than through any conventional outgassing process. This idea, while undeniably captivating and widely covered in mainstream media at the time, represented and continues to represent a distinctly minority position within the broader scientific community. The overwhelming majority of astronomers and astrophysicists who studied Oumuamua's data have consistently maintained that the object's behavior, while genuinely unusual and not yet perfectly explained down to every last detail, remains fully consistent with a natural, if unusual, icy body, particularly given that subsequent research increasingly favors the hydrogen ice or nitrogen ice sublimation models as the most likely explanation. Nevertheless, the artificial origin hypothesis captured enormous public imagination, and it's a large part of why Oumuamua remains such a widely recognized, frequently discussed object even years after it became too faint to observe. It's worth being genuinely clear here about what nobody knows why actually means in the context of this story, because the phrase can be misleading if taken too literally. Scientists do have several credible, physically plausible natural explanations for Oumuamua's observed acceleration, and the hydrogen ice sublimation model in particular has gained substantial support within the research community as a leading candidate. What remains genuinely unresolved, and likely will remain unresolved indefinitely, is which specific explanation is actually correct, since Oumuamua became too faint to observe in detail not long after its discovery, and it is now on a permanent, one-way trajectory out of our solar system, meaning astronomers will almost certainly never get another opportunity to directly study it and definitively test these competing theories. This is the heart of what makes Oumuamua's story so genuinely frustrating and so genuinely fascinating for scientists. We caught only the briefest possible glimpse of an object unlike anything ever confirmed before, gathered just enough data to know that something interesting and not fully explained was happening, and then watched it disappear back into the depths of interstellar space before we could gather the additional observations that might have settled the question once and for all. To understand just how narrow this observational window really was, it helps to walk through Oumuamua's actual timeline through our solar system. It was first detected in October 2017, several weeks after it had already made its closest approach to the Sun, meaning astronomers essentially caught it on its way back out, rather than on its way in. By the time it was discovered, it was already moving away from both the Sun and Earth at tremendous speed, giving researchers only a matter of weeks to gather as much data as possible, before it became too faint for even the most powerful telescopes of the time to track in useful detail. It passed the distance of Jupiter's orbit by early May 2018, crossed Saturn's orbital distance by January 2019, reached the distance of Uranus's orbit by August 2020, and passed Neptune's orbital distance by around June 2024. According to current projections, Oumuamua is expected to reach the outer edge of the Kuiper Belt around late 2025 and won't reach the heliopause, the boundary marking the true edge of our solar system's influence, until November 2038. Today, Oumuamua sits at a distance of more than 100 astronomical units from Earth, meaning more than 100 times the distance between Earth and the Sun, continuing to head outward toward the constellation Pegasus, and it is, for all practical purposes, permanently lost to direct observation. Even instruments as powerful as the James Webb Space Telescope, which didn't even exist yet when Oumuamua was first discovered, are simply unable to pick out an object this small, this dim, and this far away, making any further direct study of it essentially impossible using current or currently planned technology. Given how much frustration this brief observational window has caused within the scientific community, it's perhaps unsurprising that Oumuamua's passage directly inspired renewed serious interest in developing better tools and strategies for studying future interstellar visitors more thoroughly. Researchers have proposed various concepts for spacecraft missions specifically designed to intercept and study future interstellar objects, potentially even attempting a direct flyby or rendezvous mission if a suitable object is detected early enough and with a favorable enough trajectory. One such concept, sometimes referred to as Project Lyra, has explored the theoretical feasibility of eventually sending a spacecraft to catch up with Oumuamua itself, though researchers acknowledge that any realistic mission along these lines would likely require a launch sometime in the 2030s, using advanced propulsion techniques like a close solar flyby maneuver to build up sufficient speed, with an expected arrival at Oumuamua's location not occurring until sometime around 2048. Decades after its initial discovery, highlighting just how difficult and resource-intensive actually chasing down one of these fast-moving interstellar wanderers would truly be. In the meantime, newer and increasingly powerful survey telescopes coming online around the world are dramatically improving astronomers' ability to detect future interstellar objects much earlier in their approach, potentially giving scientists a far longer, far more scientifically productive observation window the next time an object like Oumuamua passes through our solar system. This brings us to a particularly relevant and important point of comparison. Oumuamua wasn't actually the last interstellar object astronomers have detected. In August 2019, astronomers discovered a second interstellar visitor, an object named Borisov, which behaved much more conventionally, displaying a clearly visible coma and tail consistent with a fairly typical comet, offering researchers a far less ambiguous, more straightforward case study by comparison. And more recently, in July 2025, astronomers detected a third confirmed interstellar object designated 3I Atlas, which has itself displayed a range of genuinely unexpected behaviors, including unusual chemistry and puzzling changes in brightness, giving scientists an unusually extended opportunity to study interstellar material in detail, precisely the kind of extended observation window Oumuamua never afforded researchers back in 2017. Comparing these three objects side by side has proven enormously valuable to astronomers, helping to establish a broader context for just how unusual, or how relatively typical, Oumuamua's specific behavior actually was, relative to interstellar objects more generally. Some researchers now suspect that Oumuamua's genuinely unusual characteristics, its extreme shape, its complete lack of a detectable coma despite measurable acceleration, may reflect the fact that it happened to be an unusually small, unusually fragile object, one that may have been significantly altered, weathered, or even partially fragmented during its exceptionally long journey through interstellar space, rather than necessarily representing what a typical interstellar object should look like. It's also worth addressing directly why so much confusing, inaccurate information about Oumuamua continues to circulate online, sometimes years after the object itself became impossible to observe. Part of the explanation lies simply in how compelling and mysterious the original story genuinely was: a strange, cigar-shaped object from another star system, behaving in ways that stumped some of the world's leading astrophysicists, with at least one prominent Harvard scientist publicly floating the possibility of artificial origin. This combination of genuine scientific mystery and tantalizing speculative possibility has made Oumuamua a recurring subject for sensationalized articles, misleading social media posts, and outright fabricated claims, particularly the kind of viral posts falsely suggesting the object has recently returned or changed course again. Despite the well-documented fact that Oumuamua is now moving steadily and permanently away from our solar system with absolutely no credible observational evidence suggesting otherwise. Responsible science communication requires clearly distinguishing between the genuine, well-documented mystery surrounding Oumuamua's original 2017 trajectory anomaly and the false, unsupported claims about supposedly new behavior that continue circulating online, often stripped of any real context, sourcing, or scientific credibility. It's also worth taking a moment to appreciate just how much scientific debate this single, brief observation generated within the professional astronomical community, because it illustrates something important about how science actually works when confronted with a genuinely novel, poorly understood phenomenon. In the months and years following Oumuamua's discovery, dozens of peer-reviewed papers were published attempting to explain its unusual acceleration, its extreme shape, and its lack of a detectable coma, with researchers proposing and testing a wide range of hypotheses against the limited but genuinely puzzling dataset available. This kind of vigorous, sometimes contentious scientific debate isn't a sign that something is wrong with the scientific process. It's actually a sign that it's working exactly as intended. When a genuinely novel object defies easy categorization, the appropriate response isn't to immediately settle on a single explanation, but rather to rigorously test multiple competing hypotheses against the available evidence, gradually narrowing down the most plausible explanations while remaining honest about the genuine uncertainty that remains. The fact that the hydrogen ice and nitrogen ice sublimation models have gained more support over time, while the far more radical artificial origin hypothesis has remained a distinctly minority position, reflects this normal, healthy process of scientific refinement playing out over several years of careful analysis and debate. It's also worth understanding a bit more about how researchers actually calculated Oumuamua's non-gravitational acceleration in the first place, since this measurement forms the entire foundation of the mystery. Astronomers tracked Oumuamua's position across dozens of individual observations collected by multiple different telescopes around the world over the course of several weeks, carefully comparing its measured position at each observation against the position predicted by standard orbital mechanics, accounting for the gravitational influence of the Sun and all the major planets in our solar system. The discrepancy between these predicted and observed positions was small, but it was consistent, and it grew larger over time in a pattern precisely matching what researchers would expect from a weak continuous thrust pushing the object away from the Sun, exactly the kind of subtle but measurable effect produced by comet-like outgassing. This kind of careful, statistically rigorous trajectory analysis is a well-established technique within astronomy, routinely used to detect similarly subtle non-gravitational effects in comets throughout our own solar system, which is precisely why astronomers felt confident enough in the measurement itself to treat the resulting mystery as a genuine scientific puzzle, rather than dismissing it as some kind of simple measurement error or statistical fluke. Given how much attention Oumuamua's story received during its brief period of visibility, it's also worth noting how this single object influenced the broader field of planetary defense and near-Earth object tracking more generally. Even though Oumuamua itself never posed any danger to Earth, given its trajectory carried it nowhere close to our planet, its discovery highlighted just how easily an object of this kind could pass through our solar system with only weeks of advance warning, using telescope technology that existed back in 2017. This realization helped strengthen the case for developing more sensitive, wider-field survey telescopes specifically capable of detecting faint, fast-moving objects earlier in their approach, technology that has since proven directly valuable in enabling the far more extensive observation campaigns conducted for both Borisov in 2019 and 3I Atlas in 2025, each of which benefited from lessons learned and technology improved in the years immediately following Oumuamua's brief, frustratingly incomplete visit. It's also worth reflecting on how Oumuamua's story has been shaped and occasionally distorted by the sheer scale of public fascination it generated. Very few astronomical discoveries in recent memory have captured the popular imagination quite the way Oumuamua did, spawning countless documentaries, magazine features, university lecture series, and even entire popular science books dedicated to unpacking its mystery. This level of sustained public interest is, in many ways, a genuinely positive thing for science communication, drawing new audiences into learning about orbital mechanics, cometary physics, and the broader search for interstellar material. But it has also created fertile ground for exaggeration and misinformation to spread, particularly online, where dramatic, attention-grabbing claims about Oumuamua returning or changing course again tend to travel far more widely and far more quickly than the more measured, technically accurate explanations favored by the scientific community. This is precisely why maintaining a clear, evidence-based understanding of what actually happened with Oumuamua, separate from the various embellishments and outright fabrications that have accumulated around it over the years, remains so important for anyone genuinely interested in understanding this remarkable, still partially unexplained visitor from beyond our solar system. It's also worth reflecting on how Oumuamua's story has been shaped and occasionally distorted by the sheer scale of public fascination it generated. Very few astronomical discoveries in recent memory have captured the popular imagination quite the way Oumuamua did, spawning countless documentaries, magazine features, university lecture series, and even entire popular science books dedicated to unpacking its mystery. This level of sustained public interest is, In many ways, a genuinely positive thing for science communication, drawing new audiences into learning about orbital mechanics, cometary physics, and the broader search for interstellar material. But it has also created fertile ground for exaggeration and misinformation to spread, particularly online, where dramatic, attention-grabbing claims about Oumuamua returning or changing course again tend to travel far more widely and far more quickly than the more measured, technically accurate explanations favored by the scientific community. This is precisely why maintaining a clear, evidence-based understanding of what actually happened with Oumuamua, separate from the various embellishments and outright fabrications that have accumulated around it over the years, remains so important for anyone genuinely interested in understanding this remarkable, still partially unexplained visitor from beyond our solar system. Stepping back from the specific details of Oumuamua's trajectory puzzle, it's worth considering why this single object, one we only observed for a matter of weeks, continues to matter so much to scientists studying the broader universe. Before Oumuamua's discovery, the existence of interstellar objects passing through our solar system was purely theoretical, predicted by astronomers based on general models of how planetary systems form and eject leftover material, but never actually confirmed through direct observation. Oumuamua changed that permanently, providing the first hard, undeniable evidence that material from other star systems really does occasionally drift through our own cosmic neighborhood, and its strange, still not perfectly understood behavior has directly shaped how astronomers plan, prepare for, and interpret every subsequent interstellar detection, including Borisov and 3I Atlas. In many ways, Oumuamua functioned as a kind of scientific wake-up call, revealing that our solar system isn't the isolated, self-contained system many people once implicitly assumed, but rather one small part of a much larger, more interconnected galaxy, one where material and potentially information about the conditions present in other planetary systems occasionally drifts across unimaginable distances before briefly passing through our own backyard. As we bring this video to a close, it's worth sitting with just how strange and genuinely open-ended this story remains, even years after Oumuamua first captured the world's attention. A small, oddly shaped fragment of some other star system formed under conditions we may never fully understand, drifted silently through interstellar space for what may have been millions or even billions of years, before briefly, unexpectedly swinging past our own sun, behaving in ways that didn't perfectly match any category scientists had prepared for, and then disappearing forever, back into the depths of interstellar space, before researchers could gather enough data to settle the question definitively. The most likely explanation remains a natural one, almost certainly some form of efficient, largely invisible outgassing, driven by exotic ices like frozen hydrogen or nitrogen, but the honest, scientifically accurate answer is that we may never know for certain, precisely because Oumuamua is gone and it isn't coming back. If you enjoyed learning about this genuinely fascinating cosmic mystery, make sure to like this video, subscribe to the channel for more deep dives into space and astronomy, and let us know in the comments which explanation you find most convincing. Hidden hydrogen ice, nitrogen sublimation, some other natural process we haven't even considered yet, or do you lean toward the more speculative minority theory that Oumuamua might not have been entirely natural after all? We'll see you in the next video with another incredible story from the far reaches of our solar system.